Hi, this is Dan Detmeyer with Amphenol Broadband Solutions. Welcome to our Fiber 101 training series. In this series, we're going to have multiple sessions covering the basics of fiber. In this first session, we'll have the fiber introduction and fiber optical theory. As we go through this training, the chat will be open, so if you have any questions, feel free to put those in the questions section, and at the end of this, we'll address all the questions. Let's get started. Fiber optics is pretty basic. It's pretty similar to our RF system. It's just going to be a transport for our signals to get from one location to another. As an example, from the head end to a node or a hub or the customer's end device. What we're going to be looking at here is we actually have an optical transmitter. This could be located in the head end. It's actually converting the RF signal into a light pulse. And this light pulse actually takes the signal and injects it into the fiber optic cable. This fiber optic cable transports it to the optical receiver, which in turn takes that light pulse and converts it back into RF energy. Let's take a look at the evolution of fiber optics. What we're looking at here is amplifier cascades. When we first started out, we only had analog video, which was for entertainment purposes to watch video services such as ESPN, Showtime, HBO, things like that to the end consumer. We had a long cascade of amplifiers. This actually started at the head end where the signals were received. And we went down these cascade of amplifiers that could be 30, it could be 70 amplifiers to the end consumer. With these amplifiers, they actually created noise and distortions on each amplifier. So as we went down the cascade, it would get worse. So the customer that was at the very beginning of the cascade would have a very decent picture. As it went down the cascade, the customer at the end, their picture could be a little bit degraded. With these long cascades that we had with the analog video, the noise and distortion was too great for these advanced services to work properly. So next in the evolution came HFC system, hybrid fiber coaxial cable system. Started to get into high-speed data, voice, and this required a two-way communications, not only going from the head end to the customer, but from the customer back to the head end. In this case here, I'm showing a node plus 4, which basically means after the node, we have 4 active devices. You might have had a little bit more active devices, and then it fed the customer. So that was good when we first started out with these advanced services. So with the 1 gig services, we actually needed a cleaner signal. So with that advent, we actually went to the node plus 0. So we actually took the fiber into the neighborhood where the customers were, and all we had was passive devices versus amplifiers after the node. So this reduced the noise even further. And then as we're advancing in services, this is where the fiber to the home comes into play. So now we're taking this fiber signal, going from the head end all the way to the side of the customer's home, or even inside the customer's home with different PON services. Here I'm showing a piece of fiber optic cable. This is a single strand. It's made up of 3 components: the core, the cladding, and the coating. The core is a silicone glass. This is where the light is going to be transported through. Around that core is the cladding. With that, that's going to help contain the light in the core. And then over the cladding is a coating. This coating is there just for protection, nicks, dings, moisture, things like that. Now, when we start looking at fiber optics, we're talking about light. In the cable industry, we're used to dealing with frequencies. Here I'm showing a spectrum, and we're going from the AC on the far right up to gamma rays. This is where the Incredible Hulk stuff is. Now, when we start looking at this in the cable industry, we're used to frequencies. You know, our TV signals were in megahertz. So when we started looking at this, we were very comfortable with megahertz, gigahertz, kilohertz. Now, when we start getting into the light, this is where it changes a little bit. We're going to start dealing with wavelengths. And when we're starting to deal with wavelengths, there's a relationship between frequency and wavelengths. Here I'm showing a sine wave. Now, when we start looking at what a frequency is, it's the number of cycles in 1 second that you're going to be seeing. So when we're talking about TV signal in the megahertz, that's millions of cycles in 1 second. And that's what we're used to. When we start getting into wavelengths, we're actually looking at the distance from one peak to the next successive peak there, and that's the actual wavelength. And the relationship here is that with the lower frequencies, we actually have the longer wavelengths, and then when we get over to the left, we have the higher frequencies but the shorter wavelengths. Here we're looking at AM signals. This is a kilohertz. It might be AM radio, talk radio. And in here, we're actually looking at the wavelength of a football field. So that's a pretty long distance. But then when we started looking at the megahertz, we're looking at 1 meter, or 3.3 feet in length. When we're looking at gigahertz, we're looking at 4/10 of an inch in the wavelength. When we start looking up at X-rays, it's 30 times the diameter of a hydrogen atom. That's just crazy stuff there. And then next we have the visible light spectrum. This is from 400 nanometers to 700 nanometers. This is what we see with our eyes. This is how we can see different objects with the light reflecting off these objects. Next we go to the infrared area. This is where the optical fiber wavelengths reside. This is from 860 nanometers to 1625 nanometers. It would be nice to be able to see the visible light in our fiber cable. But when you start looking at it, when we look at the fiber wavelengths that we're using, our popular wavelengths are 1300 nanometers to 1550 nanometer wavelengths. And this is in the infrared area. We can't see this, but with this area here, this is where it has the least amount of attenuation to our wavelengths. So that's one reason that we use those. And these two wavelengths that we're looking at here, the 1300 and the 1550, later on we're going to be seeing why we actually use these wavelengths. Longer wavelengths require less energy for transmission than the shorter wavelengths. When light strikes an object, one of three things happens, and often together. The light is reflected, absorbed, or refracted through the object. Here we're looking at absorption. We're showing two objects, a white ball and a black ball. The light waves, when it hits the black objects, it'll be absorbed. We've all heard of a black hole, very similar. When it hits the white object, most of the light reflects off, it's not absorbed. With reflection, some of the energy never enters the object it strikes. It's reflected from the surface. All surfaces reflect some light, and in different amounts, and this is why we see the colors we see. The light that's not absorbed or reflected is refracted. With refraction, the wavelengths actually change speed, and by changing speed, they actually change direction. We've probably all seen it where you put a stick into the water and it's distorted. It actually looks like it's going to the side. So that's just the difference in speed of the wavelengths, which changes direction as it goes through the different objects. Those objects that you can see through, they're referred to as transparent. Here I'm just showing a pane of glass. All objects absorb, reflect, or refract some of the wavelengths more than others. That's why we see colors. Objects that appear blue look so because they reflect more of the blue light than other wavelengths. Refraction occurs when the light waves change speed as they travel between two different materials, each with a different index of refraction. From the air, it's traveling 186,000 miles per second. Once it hits the glass, it actually slows down to 125,000 miles per second. And then once it passes through the glass and gets back into the air, it can travel again at 186,000 miles per second. Now, by doing so, at the same time, it actually changes direction. When it hits the air at a higher index of refraction, it actually changes speed to 125,000 miles per second. But once it goes back into the air, it starts traveling 186,000 miles per second again. So you can see it actually changes direction. When we start looking at the index of refraction, the vacuum is what we actually use as our reference. And that's traveling at 186,411.36 miles per second. And that index of refraction is 1. When you start looking at air, it's a little bit slower. Index of refraction is 1.003. When we start looking at water, it's 158,000 miles per second with an index of refraction of 1.3. If we go down to the optical fiber cladding, that has a speed of light of 127,676 miles per second with an index of refraction of 1.46. Now, if you go to the optical fiber, the speed of light actually slows down. It goes to 126,810 miles per second. and has an index of refraction of 1.47. When I first saw this, I thought it was kind of strange. I thought there was an error here because our light is actually traveling through the core of the optical fiber. So wouldn't we want that to go faster than the cladding? So when we start looking at this in just a couple slides, we're going to be seeing why the optical fiber core has a higher index of refraction than the cladding does. So here we're looking at an object in the water, and it appears pretty close, and you probably all experienced this. You see a rock, you're like, hey, that's kind of a neat rock, I'm going to go grab that. And then you put your arm in the water, and you're going way deeper than you expected. Similar here. Here I'm showing a circle. It's a little bit distorted there, but that's because it's refracted in the water. And when you actually start seeing the actual location, this is what you see. So the object that is refracted actually appears closer than reality. So the principles that cause the object in the water to seem closer or look bent are the same principle that keep the light contained in the optical core of the fiber. So here we're showing the fiber optic core in blue, which is a dense medium, and the cladding, which is a less dense medium. Here we're injecting light, and we're going to hit it at a certain angle. This is going to be called the angle of incident. And once we hit the angle of incident, it's going to refract away from the normal line. The normal line is just 90 degrees to the surface of these two mediums. Once we get to the angle of incident of 42 degrees, now the light is refracted and it's parallel with the surface of the core and the cladding. When the angle of incident reaches a value known as the critical angle, the refracted rays travel along the surface of the medium and are refracted to an angle of 90 degrees. If we can just increase this angle of incident just a little bit above 42 degrees, now these light waves, as it hits the junction between the cladding and the core, it's actually going to be refracted and reflected back into the core. This is what keeps the light in the core of the fiber optic cable. Here I'm showing a single strand of fiber made up of the core, the cladding, and the coating. So in cable TV, we're used to working with coaxial cable, which is a lot larger. So when you start looking at fiber optic cable, twice the size of a human hair, you might start freaking out a little bit, but when you start looking at putting connectors on, things like that, it becomes pretty simple after you do it a few times. When you start looking at the core and the cladding, this glass is made from extremely pure silicon dioxide. And different amounts of dopants are put into the different core and the cladding to make the core a denser material or a higher index of refraction than the cladding. And that's what keeps the light in there. So as long as we maintain that critical angle of greater than 42 degrees, that's going to keep the fiber optic wavelengths within the core of the fiber optic cable. So the top two images would be correct. When you look at the bottom image, this light is going at a steep angle, and now it's being lost up into the cladding and into the coating. So this is attenuation or loss. There's two types of fiber optic cable, single mode and multimode. The top image here, I'm showing a multimode. Now mode only means the number of paths that the light wave will take. In the multimode fiber, the actual core is very large. It's 50 to 62 microns. When you start looking at this, it can have multiple paths. Multimode fiber, this is used more in data centers. It has a little bit higher loss and doesn't travel as far. The bottom image, we're actually showing a single mode fiber optic cable. This is what's used primarily in the cable industry. The core is 8 to 10 microns, very small, and there's only room for one light path. So as the wavelengths are going through there, it's only taking a single path. Again, this is what's used mostly in the cable industry. Next, we're going to talk a little bit about attenuation. Here I'm showing a single strand of fiber optic cable. We got the core, the cladding, and the coating. Now, if you bend the fiber optic cable too sharp, what happens is that light wave is now beyond that critical angle, and it actually escapes through the cladding and up into the jacket. That's called macrobending. This light that escapes is actually called attenuation, so that's loss. So again, as you're handling this fiber optic cable, make sure that you handle it properly, and make sure you have a nice sweeping bends. The next thing we have is microbending. And this occurs when you're actually bending this at a very sharp angle. And this is due to probably when you're closing the lid of a node. Be careful in how far you actually bend that fiber optic cable. And this can also occur if you're actually tie wrapping the fibers too tight in a bundle. So be careful. You don't want microbending. Again, that's very high loss. So the other thing we have is absorption. Even the purest materials have some sort of attenuation to them. This is imperfections inside the cable itself, and the light is actually absorbed, which equates to loss and attenuation. I kind of relate it to sunglasses. In order to reduce the intensity of the light, the light hits the sunglass lenses and it's reduced. So it's just loss, again, absorption. The other type of loss is called Rayleigh scattering. And this is caused by atomic structures and particles in the fiber that reflect the light that hit them. Here in this video, you're seeing the different impurities. And as the light strikes those impurities, it reflects that light up into the cladding and into the coating of the fiber optic cable. And this is loss, this is attenuation. Let's look at the attenuation curve of fiber optic cable. Attenuation is the combination of the effects of absorption and scattering in a fiber. Here we're going to plot the attenuation curve. The bottom of the graph, this is the wavelengths in nanometers, from 800 to 1800 nanometers. Over on the left is the loss in dB per kilometer. So it's going to be 0 at the bottom and 2 dB per kilometer on the left. Now this is a little bit different from coaxial cable, where we're looking at the loss per 100 feet of coaxial cable. With fiber optic cable, it can go a long distance. So we're looking at loss per kilometer. So first we'll look at the Rayleigh scattering. At the shorter wavelengths, it has a lot of attenuation, up about 2 dB. But as it starts to come down, now that we get into the wider wavelengths, we actually start seeing low attenuation. So around 1800 is very low, a couple tenths of a dB. So when we look at the absorption loss, it's following the same pattern as the Rayleigh scattering did for the attenuation. But once we get to about 1300 nanometers, then it actually starts bumping up, higher loss. Then it drops back down about 1500 nanometers. At 1310, we're looking at about a loss of 4 tenths of a dB. 1500 nanometers, we're looking at about 3 tenths of a dB, which is very small loss. But you can see this little bump up there. Now earlier on, we talked about 1310, 1550 as being very common wavelengths that we use in the cable industry. And this is why, because it has less attenuation, and we avoid that high loss that bumps up between 1300 and 1550 nanometers. Next, we're going to talk about dispersion. And dispersion is the spreading of the light as it travels away from the source. Here I'm showing a flashlight. And with the flashlight, when you turn it on, the beam doesn't go straight out like this. It actually starts to flare out and spread as it travels away from the flashlight. So this is dispersion. So with dispersion, this is the spreading of the light as it travels away from the source. So here I'm actually showing a fiber optic cable, and I'm showing a pulse of light in the top slide there. These pulses of light, as they travel from the transmitter, they might spread out a little bit, but as long as the pulses are distinguished at the receiver, we can take that information and reconvert it into the electrical signal. Now with dispersion, if this starts to spread out too far, what happens is by the time it reaches the receiver, it's combined together with other pulses, and you can't distinguish what the signal actually was. So this is where you start getting errors. So let's look at dispersion. We'll actually plot this like we did with the attenuation. Now a little bit different here. We're going from 800 nanometers to 1700 nanometers on the bottom. And on the left, in the center, we have the zero dispersion point, where there is no dispersion. Up on the left, on the top, this is where we have positive dispersion. This is where the longer wavelengths travel faster. Down at the bottom, this is where we have negative dispersion. This is where the shorter wavelengths travel faster. So as we start plotting this, what you'll see is that it does have the negative dispersion in the shorter wavelengths, but as it hits about 1300 nanometers, what you're starting to see is there's zero dispersion. And then past that point, now we get into a positive dispersion loss. So again, our magic number, 1300 nanometers. So we use this wavelengths quite a bit, again because of attenuation, but also we have very low dispersion at that wavelength. Now the 1550 was also a popular wavelength that we use. So the manufacturers, what they do is they can actually produce this fiber optic cable to have zero dispersion at 1310 and 1550. That concludes the training on the fiber optic introduction and the fiber optic theory. So I see there's been questions coming in, and I'm going to take a couple seconds to go over to my desk to get to my computer so I can actually see the questions. And in the meantime, if you have any additional questions, feel free to put them in the chat.
All right. Let me look and see what kind of questions came in on the chat here. We got a couple of them. The first one is, how is it possible for the light to travel fast through the air and then slow down when it hits the glass in your example and then speed back up? Yeah, that's a good question. It was explained to me that the way this actually works is kind of related to like a highway with 4 lanes of traffic. So you're going 65 miles an hour down there, there's no traffic. But then all of a sudden there's congestion. And during that time, you can still go 65 miles an hour, but now you have to change lanes, maybe going from the first lane up to the 4th lane and then back to the 3rd and so forth. So you're still doing the same speed, but you're going through these obstacles that actually you're going a further distance, so you're slowing down a little bit. And then once you're past that congestion, now you can keep on going 65 miles an hour. So hopefully that answers that question there. The next one that we have here is if a fiber gets pinched between the housing and the lid of a node and has high loss, will just straightening out the fiber fix it again? And that's kind of a, don't know. It could be either way. One thing, it depends on how smashed that fiber actually was. So you could just pull it out, straighten it out, look at your power level, just make sure it's not fluctuating, move the fiber a little bit, and where it was pinched, and make sure that it's not fluctuating. But in the second part, we're going to be doing multiple parts of this Fiber 101. The next session is going to be about cables and connectors. And in that session there, we're talking about the optical fiber itself, and it can be brittle. So if you take it too far and it's actually broken there, then you'd have to repair that, put a connector on there or use a spare fiber. So hopefully that answers that question there as well. So those were the only 2 questions I saw in the chat. As I mentioned before, hopefully, you got something out of this session. We're going to be doing multiple sessions. The next session is going to be coming soon. It's going to be covering cables and connectors. In the meantime, if you do want to find any more information, we have a lot of resources on our website at amphenolbroadband.com. Please go there for any resources. We have additional videos on just Cable 101, our different products, and we'll be putting the fiber videos up there as well. So with that, look forward to the next session that'll be coming soon. And until then, I'm Dan Detmeyer with Amphenol Broadband Solutions, and we'll talk to you next time. Thank you.